This is SpaceTime, Series 19, Episode 94, for broadcast on the 30th of December 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, a galaxy supercluster discovered hiding behind the Milky Way, the number of known black holes expected to double within 2 years, and a leap second to be added on New Year's Eve. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
One of the largest structures in the known universe, a giant previously undetected galaxy supercluster, has been discovered blocked from view by the bulk of our Milky Way galaxy. A report in the monthly notices of the Royal Astronomical Society claims the newly found Vela galaxy supercluster may help explain the difference between the measured motion of the Milky Way through space and the motion it should have based on the distribution of previously mapped galaxies. The large-scale structure of the universe comprises an intricate network of galaxies, galaxy clusters, and galaxy superclusters like Vela, which form the filaments and connecting nodes surrounding massive empty voids to create a cosmic web. The Milky Way, together with Andromeda, which dominate our local group of galaxies, is located along one of these thin filaments. Galactic superclusters are formed at the connecting nodes where the filaments intersect. One of the study's authors, Professor Matthew Collins from the Australian National University, says the Vela supercluster appears to be one of the largest concentrations of galaxies in the known universe. However, he admits further studies are needed in order to confirm the findings. The Vela supercluster is far larger than Laniakea, which is the supercluster to which the Milky Way belongs. Laniakea, which contains 100 million billion stars and whose name means immense heaven in Hawaiian, was discovered back in 2014. Astronomers found that our local group of galaxies resides towards the outskirts of the half-billion light-year-wide Laniakea, which encompasses some 13 major galaxy clusters, including both the Virgo cluster and the Great Attractor, the gravitational centre of Laniakea, and which is a giant mass comprising both the Norma galaxy cluster and the Hydra Centaurus constellation. On an even larger scale, the Laniakea supercluster appears to be falling towards the Shapley concentration of galaxies. The newly discovered Vela supercluster appears to cover an even larger area of the sky than Shapley, but had previously gone undetected because it's on the other side of all the stars, gas and dust which make up the Milky Way. The authors discovered the Vela supercluster by using the Anglo-Australian telescope at Siding Spring to measure distances to galaxies on the far side of the Milky Way. Their findings allowed the authors to confirm earlier predictions that Vela was indeed a supercluster. The study also helped to estimate the supercluster's effect on the motion of the Milky Way. 2 new Australian surveys in 2017 will work to try and confirm the ultimate size of the Vela supercluster. The Taipan Optical survey will measure galaxy distances over a bigger area around Vela. And the Wallaby Radio survey will enable astronomers to peer through the gas and dust in the densest parts of the Milky Way, allowing them to see into the very heart of the giant Vela supercluster. Collis says the newly discovered supercluster is a massive galactic collection, covering an enormous chunk of the sky that's simply been hidden from view until now.
Well, the Vela supercluster is an enormous, great collection of galaxies and clusters of galaxies that covers a big chunk of the sky and is at about 800 million light-years distance from us, which consists of perhaps 100,000 galaxies. And we've been looking for something like this for quite some time, so it's very exciting to actually discover it now.
Okay, you say you've been looking for it for some time. That must mean that you've seen something in the way, well, maybe our galaxy and others in our local area are moving, which has sort of hinted that there's something being hidden by the bulk of the Milky Way.
Something has been pulling our Milky Way and the local group of galaxies in that direction. And although we've tried to add up the effects of all the different structures in the sky, we've still been missing a sizable fraction of that motion. And we've been wondering what big mass is actually being pulling us in that direction.
A supercluster is a pretty huge object, even on cosmic terms. How come no one ever noticed it before?
Well, it's been hiding behind the plane of the Milky Way. All the gas and dust and stars that make up our Milky Way have actually been hiding this enormous concentration of galaxies from us. And it's only recently, with the advent of good infrared and radio imaging of the sky, that we've begun to suspect that there's been this massive concentration there. And so we've been looking behind the plane of the Milky Way, peeking through the gaps in the gas and the dust and the stars, trying to find out what's there. And recently, we've actually realized that two big concentrations of matter either side of the Milky Way actually join up behind the Milky Way. And there is, in fact, another massive supercluster there, like the very massive Shapley supercluster, which is in a similar part of the sky. And this, it looks, might be able to explain the missing motion that we've been looking for the last 10 years or more.
Now, the last time we looked at superclusters on the precursor to space-time star stuff was when we discovered Laniakea back in 2014. How does this compare to Laniakea, and is one a part of the other, or are they in different locations?
So Laniakea is the local supercluster. It's the supercluster that actually contains and encloses the Milky Way and all the local galaxies around it. This is much further away. This is a distinct supercluster. It has its own identity, and it's also much bigger than Laniakea. Laniakea is, in fact, a relatively modest supercluster. You know, we're a very ordinary spot in the universe. We're on an average planet around an average star in an average galaxy, and as it turns out, we're in an average supercluster, whereas the Vela supercluster is much larger, much more massive than Laniakea.
And we're falling towards that, are we?
We are indeed falling towards it. So we're moving through space with the local group of galaxies at about 600 kilometers per second. And about 500 kilometers per second of that motion can be accounted for by things like the Virgo cluster and the Great Attractor and the Shapley concentration and various other concentrations of masses around us. But that last 100 kilometers per second that will get us from the 500 to the 600 number that we measure by looking at the cosmic microwave background has eluded us. But now it looks as if the Vela supercluster could be the last bit in that puzzle that actually makes it all close up, that actually explains why we're really moving through space at such a high velocity.
So it explains our position in the universe, doesn't it?
Well, it certainly explains our motion through the universe, and it helps us to figure out why we're moving in the way we're moving. It also helps to explain just how big structures can get in the universe. The Vela supercluster and the Shapley concentration are truly enormous structures. They're the biggest entities that are going to ever collapse down to form gravitationally bound structures in the universe. And they're the biggest entities we can see out to a very large distance from us in the universe.
So this is all part of what we call the cosmic web. How do we fit in that? Where are we in relation to this?
Well, the structures in the universe can be imagined like a sponge. The structures where there are galaxies and matter interpenetrate with the voids and empty regions of space. And there's equal amounts of voids and structures. We're actually on a tiny little filament that's falling into the Virgo cluster, which is connected to the Coma cluster and the Great Attractor in this great structure. But we're a very boring part of that. We're not at one of the major nuts. We're not on one of the empty voids, obviously. We're just on a small bump on a long filament in part of this enormous structure that pervades the whole universe.
How important is this discovery in terms of the surveys we're now undertaking? I think there are 2 new surveys starting this year.
Well, the Vela supercluster has so far, although we've discovered it, we don't yet know the full extent of it. We don't know exactly how big it is. And in order to find that out, we've got to push down closer into the Milky Way. We've got to struggle with trying to see through all the gas, dust and stars that are there. And the 2 new surveys are going to help us do that. One is an optical galaxy survey, looking at galaxies that are detected in the optical or infrared part of the spectrum and following it up with the UK Schmidt telescope at Siding Spring Observatory in northern New South Wales.
That's Taipan.
That's the Taipan survey. And then the other survey is called Wallaby, and it's a survey with the Australian SKA Pathfinder telescope. So this is a new radio telescope array in Western Australia, and because it's working in radio wavelengths, it can look right through the Milky Way, and so it can find the heart of the Vela cluster lurking on the far side of the plane of our Milky Way.
That's Professor Matthew Collis from the Australian National University. You're listening to Space Time. I'm Stuart Gary. A new detection method means the number of known black holes is expected to double within the next 2 years. Researchers from the University of Waterloo have developed a new method which they claim should detect about 10 new black holes every year, providing new clues about the history and evolution of black holes over the next decade. If correct, the study reported in the Astrophysical Journal should allow scientists to accumulate enough data in order to allow them to statistically analyse black hole properties as a population. The researchers propose a bolder approach to detecting and studying black holes, not as single entities, but in large numbers as a system, by combining two standard astrophysical tools in use today: gravitational microlensing and radio wave interferometry. First predicted by Albert Einstein's general theory of relativity, gravitational microlensing occurs when a dark object, such as, say, a black hole, passes between us and a massive background object, such as a star or galaxy. The background object's light bends around the foreground object's gravitational field before reaching the observer's telescope, making the background object appear to be much brighter rather than darker, as would be the case in an eclipse. However, even the very largest telescopes that observe microlensing events in visible light have a limited resolution, telling astronomers very little about the foreground object that's passed by. Instead of using visible light, the authors propose using radio waves to take in multiple snapshots of microlensing events in real time. When scientists look at the same event using a radio telescope through interferometry, they can resolve more than just one image. This gives them the power to extract other parameters, such as the foreground object's mass, distance, and velocity. Taking a series of radio images over time and turning them into a sort of cosmic movie of the event will allow astronomers to extract another level of information about the black hole itself. One of the study's authors, Professor Avery Broderick, says the new method has implications for the emerging field of gravitational wave astronomy and the way in which astronomers search for black holes and other dark objects in space. It should allow astronomers to study stellar mass black holes at various stages that often can extend over billions of years. The problem is black holes absorb all light and matter around them and emit absolutely no radiation, making them impossible to image, let alone detect, against the black background of space. Although very little is known about the inner workings of black holes, astronomers do know they play an integral part in the life cycle of stars, and they also regulate the growth of galaxies. Although we've been talking about black holes for over 100 years now, the first direct proof of their existence wasn't announced until 2016. That's when the Laser Interferometer Gravitational Wave Observatory LIGO twice detected a series of gravitational waves generated by collisions between merging stellar mass black holes. Broderick says scientists still don't know exactly how rare these events are, or for that matter, how many stellar mass black holes are generally distributed across a galaxy. He says for the first time astronomers will be able to place all the amazing dynamical physics that LIGO sees into a larger astronomical context. I'm Stuart Gary. This is SpaceTime. Tidal action causing ocean waves to apply a braking effect on planet Earth's rotation is being blamed for the decision to add a leap second to the end of 2016. The braking effect is caused by the Moon continuing to slowly pull away from the Earth at a rate of about 3 centimeters per year, slowing the planet's rotation in the process. As the Earth rotates, its oceans are interacting tidally with the Moon's gravitational pull. The effect is extremely small, a rotational slowdown of no more than between 0.005 and 0.002 seconds per day per century. So, while the Earth's day on average lasted about 86,400 seconds in the 1800s, today in the 21st century it's closer to 86,400.002 seconds. So, because of all this, at 23:59 and 59 seconds GMT on the night of New Year's Eve, by the way, that's actually 10:59 and 59 seconds on the morning of January the 1st Australian Eastern Daylight Time, an additional second will be added to clocks, so they roll over to 23:59 and 60 seconds GMT. That's 10:59 and 60 seconds Australian Eastern Daylight Time, before world clocks finally move another second on to midnight GMT or 11 o'clock in the morning Australian Eastern Daylight Time. Timekeeping is traditionally linked to Earth's rotation on its axis and its annual orbit around the Sun, in comparison to more distant cosmological objects. However, the 13th General Conference on Weights and Measures held in October 1967 formally changed the definition of a second from that of an astronomical description to one based on the vibration of a cesium atom, which is 9,192,631,707 periods of radiation. This increasing accuracy using cesium atomic clocks means that the brief moment in time known as the second becomes quite noticeable on astronomical scales. Around the world, time's constantly being adjusted to keep atomic clocks within 0.9 seconds of Earth's rotation. Because of this, leap seconds aren't that uncommon. In fact, we've added 28 leap seconds to our clocks since the 1970s. The last one was added at the stroke of midnight on June 30th, 2015. And technically, at our current rate of axial slowdown, we really need to be adding a leap second roughly about every 500 days. I'm Stuart Gary, and this is SpaceTime. Arianespace has wrapped up a busy 2016 with another successful launch of its heavy-lift Ariane 5 ECA rocket carrying 2 telecommunications satellites into orbit. Mission VA234 blasted off into clear blue skies from the European Space Agency's Kourou spaceport in French Guiana. The twin solid rocket boosters and liquid-fueled Vulcan 2 engine powered the 55-metre-tall Ariane 5 ECA off its tropical launch pad for the initial phase of flight.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top. Allumage EPC. Allumage des EAP, décollage.
Ariane 5 began her mission lifting off perfectly from the ground here in French Guiana with a lot of fire, beginning her mission the 11th and last this year, as the DDO says all is well on board, carrying 2 new telecommunication satellites for major regional operators. The 2 boosters are providing 90% of our thrust right now, propelling the launcher along her trajectory at an ever higher velocity. 780 tons at liftoff. She's burning 5 tons of fuel every second. That's 2.5 tons burning in each booster, plus another 300 kilos per second of fuel burning in the core stage. Ariane 5 now following the program and the onboard computer, which gives all orders, including the DDO says all is well on board. We're in the first of 4 flight phases, while heads across the Atlantic eastward. Right now, the first flight phase, the single Vulcan core stage engine and the 2 boosters are burning. Boosters will burn for another 20 seconds roughly.
The twin SRBs were jettisoned 2 minutes and 22 seconds after launch, followed less than a minute later by the payload fairing.
DDO has confirmed separation of the 2 boosters. They will fall 500 kilometers from shore into a protected area. French Guiana, in part, chosen as a base for its opening on the water. More on that. Separation is given by 2 pyrotechnic systems. We're over 100 kilometers up, and our speed a little over 2 kilometers per second. Separation of the fairing. DDO has confirmed it. Exposing to the elements our first passenger, Star 1. We can separate the fairing now because we're out of the dense layers of the atmosphere at over 100 kilometers up. There's neither friction nor heating, which could disturb the passengers. We could also discard any dead weight to maximize the launcher's operation. There are several versions of the fairing available. Tonight we're using the long one, 17 meters tall. So we are into the second powered flight phase. The boosters have done their work. Only the single lower stage engine burning now. It'll continue to burn for a total of 9 minutes. And our speed is important, because that's the role of the main stage. This cryogenic propellant system is not only highly efficient, but provides a push that can last a long time.
The Ariane 5 main stage then continued propelling the spacecraft for another 6.5 minutes until stage separation 9 minutes after launch. The Ariane 5's ESC-A upper stage then ignited its single liquid-fueled HM7B cryogenic engine for a 16-minute burn before entering the cruise phase of flight. 29 minutes after launch, the Star 1D1 telecommunications satellite was released into its geostationary transfer orbit. The Brazilian-owned Star 1D1 will handle broadcasting, broadband, internet access and other digital services over Brazil, Latin America, Central America, Mexico and the Caribbean. The 9,433-kilogram Space Systems Lourel-built satellite uses an SSL 1300 platform with 2 solar arrays generating up to 17.1 kilowatts of power. It's equipped with 18 Ka band, 28 C band and 24 Ku band transponders. The Ka band is usually used for broadband and high-speed data transmission. The C band is used for voice, TV, radio and data transmission, while the Ku band provides video transmission services directly to users as well as general internet, data and telephony communications to remote areas. The satellite carries enough fuel for a 15-year lifespan. 14 minutes after the release of the Star 1D1, the 3,400-kilogram JC-SAT-15 was deployed into its own geostationary transfer orbit. Also built by Space Systems Lourel and based on a 1300 bus, the JC-SAT-15 has a mass of just half its Brazilian counterpart. It's equipped with 2 smaller solar arrays generating roughly 10 kilowatts of power. It's equipped with Ku and Ka band transponders to supply satellite pay TV services across Japan, as well as data transfer and maritime and aeronautical services for the Western Pacific and Indian Oceans. It also carries enough fuel for a 15-year lifespan. The flight was the 90th Ariane 5 launch and the 7th this year. Ariane 5's next flight is slated for February, with the launch of the Intelsat 32E Sky Brazil 1 and Telcom 3S satellites. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter and Tumblr. Just search for SpaceTime with Stuart Gary.